Good day, grade 11. Welcome to my YouTube channel. If you're new here, if you did not subscribe, please subscribe. We're going to look at paper 2 of term 2 revision, which is its chemistry. Allow me, guys, to start with valence electron because we're going to go to the chemical bonding. Now, the valence electron, when we talk about the valence electron, you need to know at the grade 11. It's electrons in the highest energy level, right, of an atom. Right, if you know the atomic orbital, you have a nucleus, you have protons and nucleons there, and then you have those circles, we call them energy levels. So the electrons that are there at the end, at the last energy level, we call them valence electrons. Right? Okay, let's move. Now let's go to chemical bonding. The types of bonding, you need to be able to differentiate them. We have covalent bonding and ionic bonding, right? So the covalent bonding, you need to, if you know their definition, you'll be able to differentiate them. The covalent bonding, it occurs between two or more what? Or more, I'm writing what? Or more metals. As you don't have to write the table just like me, but if you want to, you can do that. The ionic bonding, it occurs between the non-metal and metal, right? And then the last point that you can, in covalent bonding, there's a sharing of electrons, and then in the ionic bonding, there's a transfer of what? Of electrons, right? Okay, guys, let's go to Lewis structures. Lewis structures, guys, go to my other video and see the Lewis structure, but I'm going to show you the Lewis structure of 2. I'm not going to add more on that. This is a cyanogen bromide. It's the same as the hydrogen cyanide. It's similar, their structure, but instead of hydrogen, there's a bromine, right? There's a bromine. It's a similar structure. The structure of the hydrogen cyanide, it's the triple bond there. It's like that, right? So it's the same as that. So the first thing that we're going to do, I'm going to draw the Lewis structure. The Br, you know the Br is in group 7. It will have 7 electrons, right? And then the Br, as you can see here, the Br is going to bond with carbon. And then here's the 1 electron of the carbon, right? And the carbon, it has 4 electrons. And then the carbon is going to share 1 electron with the Br, and then the Br is full, and then it's going to remain with 3 electrons. It must be dots, sorry. It must be dots. And then the nitrogen here, the nitrogen, it's in group 5. It will have 5 valence electrons, but it needs 3, so it's going to get 3 from carbon, and the carbon is going to share 3. It's going to share 3, so here's the 3 from the nitrogen, and then it's going to remain with 2. It's like that. It's basically like that, guys. In terms of the Cooper structure, this is the Lewis structure, guys. This is what is needed. When I say draw Lewis structure, it's this. But in the Cooper structure, it's going to be Br with 1 bond, and the carbon with a triple bond bonded with nitrogen. It will be like that. Okay. Don't draw this, guys. So now, these electrons, guys, these ones here, okay, these ones are called, and these ones are called lone pairs. So in this structure, the cyanogen bromide, there are four lone pairs. 1, 2, 3, 4. So we call these ones lone pairs, right? And these ones are lone pairs, right? And how many are they? 4 lone pairs, right? 4 lone pairs. And these electrons, these ones, we call them bonding pairs. How many are they? 1, 2, 3, 4. So it's 4 bonding pairs, right? Okay, how do we define the bonding pair? The bonding pair, is pair of electrons. It's pair of electrons shared between 2 atoms. You must be able 2 atoms to form a bond, right? You must know the bonding pairs are two electrons shared between 2 atoms to form a bond. It's very important to know that, guys. As I have mentioned that, okay, guys, here this structure, the cyanogen bromide, it's a polar molecule. How do we know it's a polar molecule? So between the carbon and the nitrogen, there will be a net dipole moment that will go that way. And then between the carbon and the bromine, there will be a dipole moment that will go that way. So guys, the net dipole moment, if you look at the arrows here, this arrow and this arrow are not the same, right? Are not the same. So the one with there is a net dipole moment here. Once there's a net dipole moment, the net dipole moment is not equal to 0. Therefore, the molecule is what? Is polar. So this molecule is polar, guys. And the shape of this molecule, is what? Is linear. As you can see, it's straight, it's linear. It's very important to understand that, guys. Let's move on. Let's see if we can have the molecule. Let's take this molecule, pH3. Guys, it's very important to understand the Lewis structure of the molecule. The central molecule will be phosphorus, and phosphorus, it's a group 5 molecule, just like the nitrogen. So it will bond with 3 hydrogens there. 3 hydrogens. So it has what? 1 lone pair. That's very important. 1 lone pair and 3 bonding pairs. 1, 2, 3, right? And 3 bonding pairs. It's very important, right? And the shape of this molecule, it's very important. It's the same as the ammonia. The shape of molecule is a trigonal pyramidal. I'm not gonna dwell why is it a trigonal pyramidal. Just need to memorize that. It's very important. Okay. Let's take this is supposed to be 2, not 3. Okay, let me take the Lewis structure of the ionic. The Lewis structure of an ionic. Let's say we have an ionic. It's an aluminium trichloride, right? So this Lewis structure, guys, it has to be 3 steps, right? It has to be three steps. Check my other video, on chemical bonding. When I draw Lewis structures, you get it there. So step number 1 here. Step number 1, you show a metal. A metal loses electrons. So here's a metal, and then you write, which is the aluminium. You write an arrow. And aluminium is in group 3. It's able to lose 3 electrons. So you write an arrow and show the aluminium lost the 3 electrons, and then you say 3 plus, right? It has lost electrons. And then you say plus 3 electrons, because aluminium is in group 3, is able to lose 3 electrons, right? So step number 2, what you do, you show chlorine. So how many chlorines are there? It's 3. You write 3 in bold brackets, and then you say 3 chlorine. And then chlorine, it's in group 7. It must have 7 valence electrons outside, right? And then you plus, what do you plus? You plus the 3 electrons that, guys, the ionic bonding. It's a transfer of electrons, as we mentioned in the definition. So the aluminium will transfer 3 electrons to what? To chlorine. So there are 3 chlorines there. Each chlorine will take each electron because there are 3 of them. So what's going to happen now? There are 3. The reason I have 3 here is because there are 3 chlorines there. So each chlorine will take 1 electron there. So it will be something like this. So it's Cl with the electrons, with the 7 electrons, plus the 1 that it has received. So each chlorine has received 1 electron from the 3 electrons there. And then it will be, now that you should show the negative, guys. Once it received the electron, do you see here? There was no charge here. Now it becomes negatively charged because it has gained the electron, right? So, no arrow here. So we show the third step. So in the third step, that's when I show this and this. Okay, let me put this in a bracket, right? That's when I'll add now these two. No, that's when I'll add these two guys, the ions. So I'll have aluminium 3 plus the 3 chloride, right? So what are you doing, Sarah, now? So what I'm doing now, I'm adding these two, this one and this one. This one, it has lost 3 electrons, and this one has gained 3 electrons. So I'm adding the 2. So what's going to happen now? These two, there will be an attraction between the two, because remember, there are 3 of these, right? And 1 of these, there will be an attraction. This attraction between the two, it's a positive and the negative. It's an electrostatic force. So what's going to form here? It's going to form something like this. So it's going to be, so it's going to, there's that. And basically this, it will be an aluminium as the central, and then there will be that. Okay, let me not draw it there. There will be that, and there will be that, and there will be that. So it's a chlorine there, and a chlorine there, and the chlorine there. So it will be that. So it will be basically that. That's an ionic compound. That's how you draw the Lewis structure of the ionic compound. Okay, let's move to, this is what you need to know, grade 11. If you're given a table, it says the table indicates the value of the bond length and the bond energy difference in hydrogen cyanide. And then we're given the bond between C and H. Is that the bond length? This is the bond. It's just C and H. And then the CN, you know it's going to be C and the triple bond. Okay, let me draw it here. So this is going to be C and H, and this one is going to be C and the triple bond. And if you see here, the bond length here, it's 0.107, and then the bond length here, it's that, right? And then the bond energy, if you look at the bond energy here, the bond energy of that. I think, guys, this is wrong. It's supposed to be the other way around, right? It's supposed to be the other way around, because a triple bond, it has a shorter bond length. Do you see? This is supposed to be shorter than this, right? So it's the other way around. The bond length are correct. The bond length are correct. The bond energy are correct. It has a higher energy. The CN, the cyanide, it has a higher bond energy and lower bond energy, right? Now it says define the term bond energy. Bond energy, guys, it's an energy needed, right? It's an energy needed. Okay, let me write it. Let me use it. It's an energy needed to break 1 mole. It's very important. 1 mole of its molecule, right? It's an energy needed to break 1 mole of its molecule to separate the atoms. Guys, I'm not going to draw that. It's an energy that is needed to break that. Now it says, explain why the bond energy of cyanide is more than the bond energy of the CH. So I'm explaining these energies here. So the reason I'm gonna explain these energies here, I'm gonna explain in terms of the bond order, right? I'm gonna explain them in terms of the bond order. So what I'm going to say here, CN has a triple bond, while CH has a single bond, right? That's how easy I'm gonna explain that. I wrote that in a, this is supposed to be here, guys, right? It's supposed to be here. No, it's correct today. Okay, now it says explain the difference between the bond length of CH and CN. So what I'm going to say, the CN, as I've mentioned, that these bond lengths are wrong. The CN has a shorter bond length than CH, right? That's simple. I'm going to now, guys, it says, will the the hydrogen cyanide, which is the molecule, the entire molecule, the hydrogen cyanide, which is the hydrogen cyanide, guys, I just showed you now, it's that molecule. Will the hydrogen cyanide be soluble in water? The question is asking, will it dissolve in water? Yes. Right? Why? Explain the answer in 2.0 by referring to the polarity of molecule. Guys, the water, okay, how I explain that? The hydrogen cyanide is polar, just like I showed you there, is polar, and also water is polar. So if they are both polar, the polar dissolves polar, right? The like dissolve the like. So if the water is polar and if the water is polar and the hydrogen cyanide is not polar, so it was not going to dissolve because it's not polar as well. If they were non-polar, both non-polar and non-polar, it was going to dissolve the like. So the polar dissolved the polar. Right, let's go to this one. This question, guys, if you look at this graph below, it shows the change in potential energy of the hydrogen atoms, which is the hydrogen and hydrogen there, approaches one another. Guys, if you look here, the atoms that belongs here at this state, guys, it's when the atoms are separated from each other, right? So the energy is approximately zero, but the energies that they have is the highest. Here at the D, they have what? Highest what energies? Highest energies. Energies, and there's the most unstable state of the elements. So here is the hydrogen, and the hydrogen, which is this here, okay, whatever. And then here, guys, at C here, guys, it's when the bond is formed. This is when the bond is formed. There's an overlapping. So this is the lowest energy. This is when the bond, okay, number one, bond is formed, right? And lowest energy. This is the lowest energy, and this is the most stable state. Most stable. They are most stable here. Most unstable state. I wanted to write state here. So here, lowest energy, most unstable state, right? And then when it gets to B or A, at B, they have high energy, but the highest energy they have, which is there's more overlapping, it's A, right? Where there's more overlapping, it's A. It's A. So this is where there's more overlapping. There's more attraction. More attraction and repulsion. It's A. Here, guys, they have highest energy state, but as a bond together, right? Okay. If you look at here, the space between here, the bond, the length between, it's shorter, and it becomes more shorter. So the bond, there's no bond that is formed there, but the distance between their nuclei, it's longer, right? Here it's short, and it's shortest, the bond length. Here they here, in order to, okay, as I've mentioned, the bond is formed, lower energy. Okay, let me note. Okay, now let's answer the question. Match the diagram 3.1, 3.3 ABC and illustrate the distance between the nuclei to the point of energy diagram. Okay, so where is the state here in the graph? Of course, it's going to be what? D here. And then, as I've mentioned, 3.1.2, where is the state where there's more overlapping there? And it's going to be what? A. That's A. And then this state is what? Is C, as I've mentioned in the graph. And then now in 3.2, what is EF? EF and FC represent. Let's look at EF. The EF represent the bond length. EF represent the bond length, right? If you look at EF from there to there, so it's the bond length. From there to there, it represents the bond length. It's very important. And then FC, it represents the bond energy. So the bond energy of C, it's going to be this energy that you read it from the graph there. So the FC is the bond energy. Bond energy. Oh, guys, I can't write energy now. Now, it says here in 3.3, which point on the graph represents the position with the greatest stability, which is the most stable state, which is going to be what? Point C, as I've mentioned. So, which is going to be this. This is the most stable, right? Which one of the letters A, C, D represented the formation of hydrogen? Give reason for your answer. Which way is the bond formed? That's when they're asking. It's also C. The reason for that, you will say it's what? Lowest potential energy. So when there's a lowest potential energy, that's when the bond is formed. Now, which factor cause the potential energy to decrease as the two atoms approach each other? What causes that, guys, is the attraction force. The attraction force causes the potential energy to decrease. So it's the attraction force between the subatomic particles of atoms. So as they approach each other through their attraction. While they attract each other, the potential energy decreases. Now let's look at this graph again, guys. This is a similar graph with that one. It says the diagram shows the energy change takes place in two atoms. They move towards each other. So guys, here, as we know, what is Y? Y is the bond length, and then X is the bond energy. So here, what does X and Y represent? So X represent the bond energy. It's very important, guys. And Y is the bond length. Bond length, right? Define the concept represented X, which is the bond length. We already done that. X, it was the bond energy. We already explained the bond energy. Guys, this is very important, this one. 2.6.3, explain the relationship between the bond order, bond length, and bond energy. So guys, you're going to start with the bond order. If they want relationship and they tell you bond order, bond, so you're going to go with this order, right? You're going to go with this order. So let's say the higher, I'll say if there's a higher, the higher the bond order. We know when we talk about the bond order, guys, we talk about the double bond, triple bond. So the higher the bond order, when we're coming from single bond to triple bond, the higher the bond order, and then we're going to talk about the bond length, the shorter the bond length. The shorter the bond length, the stronger. And then we talk about the bond energy. The stronger the bond, right? And then we're going to talk about the energy, and then and bond energy. The bond energy increases. So if something, it has a higher bond order, that means that the bond length is going to be what? Shorter, and the strength is going to be stronger, and the energy that is needed there, it's going to increase, so it's going to be higher, right? Okay, let's move to the last question, a very last question, guys. If you have this graph, guys, no? And it says, okay, let me read it. The graph below shows the result obtained during the investigation to determine the boiling points of the substances formed when hydrogen is bonded to form the group from group 5 of the periodic table. Guys, I took a screenshot of the periodic table, which is group 5 here. So these elements are from group 5. It's hydrogen bonded with them. So if you look there, there's a nitrogen there, and the phosphorus there, arsenic, and SB, which is the tin. SB, is it the tin? Yeah, I'm not sure. It's SB, whatever. Okay, guys, if you look at our graph here, it's a boiling point versus the molecular mass, which is the size of these molecules. We can see from this graph, the one with the highest size, the molecular mass is SbH3, and then followed by the AsH3, and then it's the pH3, and then the lastly it's going to be the ammonia, right? But the ammonia, since if you look at the trend here, it doesn't go with this trend. This trend, it goes this way because it's totally different from these ones. So what makes it different, the ammonia, from these ones? Because it has the hydrogen bonding. If you look at this one, none of these has the hydrogen bonding, but this one, it consists of the hydrogen bonding. So it makes different. It's different from this trend, right? This trend. right? Okay, guys, as we can see here, the greater the molecular mass, the greater the boiling point. Greater molecular mass, greater boiling point. You can see that, right? Okay. The one with the highest intermolecular force here is that one, and then followed by this one, and then this one, and this one. That's their order, because higher boiling point, higher intermolecular mass. Now the question, it says define the term boiling point. Is the temperature, guys. We need to be careful. Is the temperature in which the vapor pressure is equal to the atmospheric pressure. The temperature in which the vapor pressure is equal to the atmospheric pressure. Now it says write down the investigative question for this. Guys, the investigative question, it must be between these two. So the investigative question, it must be a question. It must be what, how, why. It must be a question you must ask. So you say, how will you talk about these two things? Those are variables, guys. So that's an independent and dependent variable. How will the molecular mass affect or influence the boiling point? And there must be a question. Or you can say, what is the relationship between the molecular mass and the boiling point? That's the investigative question, guys. There must be these two variables, the independent and dependent variable. This is the dependent and this is the independent. Right, guys, let's go to 3.3. It says consider these three. So we're going to talk about these three. Name the type of van der Waals that exists between the pH3. So the van der Waals force that exists between the pH3, it's the guys, as we have seen from this, maybe I did not mention. Okay, guys, this is a polar molecule. This is polar, right? This is the polar molecule. So it's dipole. So the intermolecular force that exists between this, it's a dipole. It's not hydrogen bonding, guys. So it's a polar molecule. So the intermolecular force that exists there, it's a dipole. So it's a dipole, right? Now the question, it says explain by referring to the shape and the polarity of the molecules. So I've explained, I've stated the intermolecular force. It's a dipole because it occurs between the polar and polar molecule. Now it says explain by the referring to the shape. So the shape of this molecule, guys, as I've explained there, it's a trigonal pyramidal. Right, it's a trigonal pyramidal, and the polarity of the molecule, it's a what? It's a polar molecule. Guys, it's exactly the same as the ammonia. The ammonia NH3, it's a polar, but it's a hydrogen bonding intermolecular force that exists there. Which three of the substance has the highest vapor pressure? Guys, the vapor pressure and the intermolecular force are inversely proportional or indirectly proportional. So what do I mean by that? The one that has the highest intermolecular force there, it has the lowest vapor pressure, right? Okay, let me say it again. I didn't hear myself. It says the question, which one of the three substances has the highest vapor pressure? Okay, guys, the one with the highest vapor pressure here is the one with the lowest intermolecular force. So the one with the lowest intermolecular force here is pH3 because it has the lowest intermolecular force. The one with the highest intermolecular force is this. And then, okay, let me put it their order. It's going to be SbH3, the first one, and then followed by SH3, and then it's going to be what? Ammonia, which is this, and then it's going to be the last one, it's pH3. So the one with the lowest intermolecular force, this is the lowest intermolecular force, and then this is the highest intermolecular force, right? It's going to be the highest intermolecular force there. So the one with the lowest intermolecular force is the one with the highest vapor pressure. So my answer will be pH3, all right? And then it says give reason for your answer. So I'll say lowest, I'll say lowest intermolecular force. That's the reason. That's my reason here, because the pH3 has the lowest intermolecular force. Now it says fully explain why SBH3 has the highest boiling point than AS. It's asking why this one has the highest boiling point than this one. So the first thing that you need to state there in 3.3, let me write the answer there. You need to talk about what you see in the graph. Do you see this one? It has the highest mass, molecular mass, and this one lowest molecular mass. So we'll say SB has the largest. It has the largest molecular mass, right? I'm going to talk about the molecular mass. That's the first point that I'm going to say. And then another thing I'm going to talk about the intermolecular force. So I'll say it has a strongest. Guys, I hope you're still following. Strongest intermolecular force, right? And then lastly, it has what? There's something that has a strongest intermolecular force. It has more energy needed to overcome the intermolecular force, right? It's very important, guys. You see, I've spoke about its molecular mass is the largest, and then if it's the largest, it has the strongest intermolecular force. And then when something has the strongest intermolecular force, that means it has it needs more energy to overcome. Okay, the last question, guys. It is expected that from the trend shown in the above, the boiling points of NH3 should fall along the dotted line, which is the boiling point of this. It's expected to go there. But why is it like that? Instead of going straight like this, it's going like that, okay? It says refer to the type of intermolecular force and explain why the NH3 does not fall there. So what is important there, guys? What is important there? You will say NH3 has the hydrogen bonding. That's what differentiates them. It has the hydrogen bonding, and then having the hydrogen bonding, that means it will have the strongest intermolecular. Guys, I was not saying this is the strongest. This is the strongest out of all. Since I was comparing between the two, it was the strongest between the two. So it has the strongest intermolecular force, and then if it has the strongest, more intermolecular force, that means more energy. Same explanation. More energy needed to overcome the IMFs, right? And then lastly, what I'm going to say there, and then hence it has the higher boiling point, right? Higher boiling point than who? Than the pH3. Guys, another thing lastly that you need to know at grade 11 is the shapes. Now let's take the hydrogen. The hydrogen, guys, it's HH. This one is, the name of the shape is what? Is linear, right? The HBr HBr, it's HBr like that. It's what? The name of the shape, it's what? It's linear. It's very important. The HCl, it's also form part of what? Of HCl, it's linear, right? Okay, now let's take the carbon dioxide. The carbon dioxide, the central molecule, it's carbon and then two oxygen. It has double bonds there. The name of the shape, it's also linear. Now let's look at the H2O. The H2O, guys, it's the H2O, it's like that. Its shape, and their lone pairs, it's the angular. It's angular or bent, right? Let's take the SO2. The SO2 here, guys, it's like that. No, the SO2, it's like that. It's like that. It's also an angular shape. Angular shape, right? It's an angular shape. And this one, okay, I'll finish up with that one. Let's look at the NH3. The NH3, the shape of NH3 is, the shape is that. So this one, it has lone pairs. It's a trigonal. It's a trigonal or trigonal pyramidal, right? Okay, and CH4, guys, look at all those shapes from your notes. It's very important to know all of them. So this one, it's a tetrahedral. It's a tetrahedral, and it's very important to know it. What else? That you need to know, guys? Look at all shapes. Look at all shapes that you need to know from the notes, and it's very important. And okay, let's look at the polarity. This one is non-polar, and this one is what? Is polar. This one is polar, and this one is polar, because they are not the same. If you look at this one and this one is the same. It's non-polar. They're not the same. This one pulls the electrons towards itself, and the same as this one. So that's why these are polar. And here, this one and the here this one. So this one is non-polar as well. Non-polar. And this one, water, obvious, it's polar. And this one is going to be polar. And then this one is polar as well. And then this one is a non-polar, right? Okay, guys, that's it. Cheers, bye.